Yes. So axi-symmetric problem is a special case of polar coordinates problem. Polar coordinates. Here, the stress function, area stress function phi. Normally, it is a function of r and theta. In the case of polar coordinates, phi is a function of r and theta. In the case of Cartesian coordinates, phi is a function of x and y. Correct? So, in axis-symmetric problem, phi is independent of theta. So that means it is function of phi is a function of only r. Only r. So here in such case the stress components will be simplified now. Stress components. So normally the stress components in polar coordinates, I have given this in the last video which I did recently. In that also I have given sigma theta and tau theta. These are the stress components. I have given the expressions for these three. If you know phi as a function of r and theta, sigma r is given by 1 by r dou phi by dou r plus 1 by r square dou square phi by dou theta square. This is the formula. Plus 1 by r square dou square phi by dou theta square. This is expression for sigma r. Sigma theta is dou square phi by dou r square. So these things you have to remember. If they ask you to find the stress components, you have to remember this. Then tau theta is given by 1 by r square dou phi by dou theta. 1 by r square dou phi by dou theta minus 1 by r dou square phi by dou r dou theta. These are the stress components in the case of polar coordinates. Polar coordinates. When phi is a function of both r and theta, you can see derivatives of phi with respect to both r and theta exist here. Correct? So this is when phi is a function of both r and theta. But axis-symmetric problem is a problem in which case phi depends only on r. It doesn't depend on theta. So these equations will be reduced still further. So in axis-symmetric problems, the stress coordinates now will be reduced to now first one sigma r. So theta term will not be there. Theta will vanish. So what is sigma r then? 1 by r into dou phi by. That's all. This term will not be there. Second, sigma theta is dou square phi by dou r square. That will be there because phi is a function of r. Third one, tau r theta will be 0. Very important. So in the case of axis-symmetric problems, there is no shear stress. Got it? Axis-symmetric problems I also now I give example. I have explained this in that video, class 17, 21 video. Suppose you take a cylinder here. It is subjected to equal uniform pressure like this. From outside as well as it can be subjected from inside also. So this is an example for axis-symmetric problem. So cylinder. Theta is theta normally we take theta like this. Is it not? This is r. This is our radius direction. This is theta direction. So in the radial direction we have stress variation, but in theta, since it is uniform, this pressure is uniform throughout the circumference, it is independent of theta. So this is an example. Similarly, hydrostatic pressure. For example, we have a body here subjected to hydrostatic pressure on either side like this. Hydrostatic pressure is equal to what? It is 0 at the top, maximum at the bottom, related to the fluids. So this is hydrostatic pressure. So here also it is an example for axi-symmetric problem. Got it? These are examples for axi-symmetric problems. And footing. Footing is a circular footing. It will once again, we assume that the load is transformed uniformly. The soil is a good soil. Then that is an example for axi-symmetric problem. So this elasticity can be used first not only structures, you can use it for geotechnical composites, all those concepts. So why I told this is these two are important. So in the case of an axi-symmetric problem, you will be having only two stress components. 2 or theta automatically becomes 0. So here the sigma is called as the radial stress because it acts along r direction. Sigma theta is called as the hook stress or circumferential stress. Circumferential or hook stress. You have learnt in strength of materials thick cylinders, Lanius equations for finding the hook stress and radial stress. Same concept. Now let me take one problem here. One problem on axi-symmetric. Prove that the stress function phi is equal to. Prove that the stress function phi is equal to. Prove that the stress function phi is equal to a log r. Prove that stress function phi is equal to a log r plus br square log r plus br square log r plus cr square plus d. This is the stress function. Solves the problem of axi-symmetric stress distribution. Problem of axi-symmetric stress distribution. So he has given the, of course here A, B, C, D, they are constants. So those constants they are evaluated using boundary conditions. Of course we are not worried about that boundary conditions now, because boundary conditions vary from problem to problem. Since in fixed cylinder problem you will have some boundary condition, rotating disc problem you have some boundary condition. So boundary conditions will differ from problem to problem. Now this is general solution for an axi-symmetric problem. Now how to prove that? So if at all you want to prove that this represents an axi-symmetric stress distribution, we have to prove tau r theta as 0, and we will find out the corresponding stress components, and we will add here and find the corresponding stress components. Corresponding stress components. So first step, to prove that it represents an axi-symmetric stress distribution, we have to prove tau r theta is equal to 0. That is the first step. Then after that we will find these two things. Simple. what is tau r theta? So tau r theta is this. So this we have to prove it as 0. So to prove this as 0, we have to differentiate that phi with respect to theta, isn't it? So is there any component? So we have here, so since phi does not contain theta term, its derivative with respect to theta will be 0. So therefore tau r theta is equal to, the formula for tau r theta is 1 by r square into dou phi by dou theta minus 1 by r into dou square phi by dou r dou theta. So here since this contains derivative theta, this also contains derivative theta, both these derivatives will be 0, therefore tau r theta is 0. Hence given phi represents axi-symmetric term. The first part is over. Simple. First part. Since it doesn't contain theta term, derivative of with respect to theta is 0. That's all. Now let us find out the stress components using the formula that we can do. So you have to use these two. Now the stress component, these two means these two. Okay? These two you have to use now. So the second part of this problem is to find the stress components. So we have proved that phi represents axis-symmetric problem. Second step, stress components. Write down the formula. Only two stress components. There is radial stress sigma r given by 1 by r into dou phi by dou r. You have phi here. Differentiate this with respect to r partially. Anyway, that partial derivative becomes total derivative. Please note that here 1 by r into dou phi by dou r is nothing but d phi by dr. Why it is d phi by dr? Because phi is a function of only r. If theta is there, then we have to go for partial derivatives. Since theta is not there, it becomes total derivative. So this is the same as, we can write here itself, this is the same as 1 by r into d phi by dr, and this is d square phi by dr. Because phi depends only on r, only one variable is there. So now what is the answer? So 1 by r into, what is d phi by dr? We have to differentiate this with respect to r. ABCD are constants. So a into derivative of log r is 1 by r. Correct? We should be knowing log r derivative is 1 by r. Plus here we have to use the product rule. U into v. That we have to use. So let me use that. So b is constant, take it outside. First function r square into derivative of second log r is 1 by r. Plus second function log r into derivative of first function r square is 2r. Yes, this is what. So I will close the that is b into that. Then plus derivative of cr square is c is constant, derivative of r square is 2r, so 2cr. And derivative of b is 0 because b is constant. So this is the first derivative. This is what? So you close the bracket. Now simplify this. 1 by r into a by r plus br multiply this plus b into 2r into log r. So it is 2br log r. Be careful here. 2br log r. This 2r is separate. Then plus 2cr. Any simplification can we do? So nothing will get cancelled. So r will get cancelled here. So this I can add a by r square. Correct? A by r square.
2b log r.
A by r square plus b plus 2b log r plus 2. So this is what we get for the. We can take b common here and we can write. A by r square plus b into 1 plus 2 log r. So this is the radial stress component. Coming to shear stress, that is hook stress or the tangential stress, hook stress or circumferential stress. So second is hook stress or circumferential stress, sigma theta. D square phi by dr square. So we have first derivative we have here. This is your first derivative, correct? D phi by dr, this thing, d phi by dr is whatever is in brackets. So this second derivative means it is d by dr of d phi by dr. That means it is d by dr of this quantity, a by r plus dr plus 2br log r plus this r. Now differentiate this with respect to r now. So a is constant, derivative of 1 by r is minus 1 by r square. So minus a by r square plus b plus 2b into, once again we have to use product rule here. R into derivative of log r is 1 by r plus log r into derivative of r is 1, then plus 2c. But it's under 1. So minus a by r square plus b plus multiply 2b, r and r will cancel, plus 2b log r plus 2c. In other words, it is minus a by r square plus 3b plus 2b log r plus 2c, or you can write sigma theta as minus a by r square plus b into 3 plus 2 log r, b I have taken in common, plus 2c. So that is the circumferential or hook stress component. So when they ask you to prove that it represents axi-symmetric problem, you have to prove tau r theta is equal to 0. Then if they ask you to find the stress components, only two stress components will be there, because tau r theta will not be there. Tangential stress or shear stress will be 0. Only will be having radial stress and hook stress. So this ABCD, they are all constants which are evaluated using boundary conditions. So boundary conditions, depending on the type of the problem, there are so many axi-symmetric problems. So depending on the this ABC, only of course D is also not there here. Only 3 constants will be there. Those 3 constants you can evaluate using the boundary conditions. This is how we have to do. This is axi-symmetric problem. So go through this 21 class also, and this will be. So those two will cover the axi-symmetric.